All right, so now we're back for part two. And so for part one, what we really looked at was this scientific machine learning, right? We looked at this problem of if we have these learnable types of methods, right? If we have these methods that can learn from data, that can learn equations and things like that, how do we use this as a scientific expert to be able to increase the speed at which we do scientific progress? And how do we use this in such a way where we can outperform the machine learning methods today by, as a baseline, using everything that they can do but adding to them, right? This is the idea behind scientific machine learning, right? So we kind of covered this. Again, we covered it really quickly. We run a whole course on this at MIT, which is like a whole semester course. So again, we really kind of just touched the surface, but hopefully we have the idea of what is the thinking behind that path, right? Now, the other path for where humans should be in the space and time of AI is in incorporating agentic AI. And I want to start to talk about this. So before I get into this, though, I'm curious, how many people here are using something like Claude Code CLI today? So yeah, it still is way less than a majority. I hope by the end of this, everyone in this room is at least set up and ready to use this, right? Because the key is that agentic AI in science is not really tomorrow, it's today. And the question is, now what I want to start with, even before I get into the more specialized tooling on this, is I want to just get everyone on the same footing to just say, how do we get started with this today? Right? Because if you're not using it today, then you're already way out of the ballpark. And I want to just get you into the space where we can start to talk about how we're improving it. But in order to get there, we got to get everyone understanding what this is, right? So just to kind of look at this, AI for software engineering has really been progressing fast. Now, again, there are some reasons to believe that it's probably plateauing because the difference that we're getting now, between like the 2025 models versus 2023 models and such, we're getting small percentage points improvements inside of the very basic software engineering benchmarks, right? So at a certain point, I would say that a lot of these tools, the best of these tools, are about at the level of a second-year undergrad, a competent second-year undergrad. But what you'll see is that having one of those around at your fingertips can be quite useful, even if that's where they seem to be plateauing, right? So we'll be talking specifically about these models like Gemini 3, Claude 4.5, and Claude 4 Opus. This is missing Claude 4.5 Opus, which will be the main one. But these seem to be the main models where anything below that, like ChatGPT 5, don't tend to do as well in this space, right? Hold on, the shoes are getting in the way. So why agentic AI actually works? So you might have, everyone at this point has probably played around with ChatGPT, right? And so if you played around with ChatGPT and you've asked it some questions, it probably got something very wrong, right? And so you're going to ask this question of, okay, why would I trust this with the code that I am writing, right? The real thing to understand for why this actually works is to understand why the agentic systems are different than just using the LLMs on their own. The real key thing is that they have a loop here, right? And this loop is write, execute, read, and fix, right? What I mean by this is what you'll see is going on with these tools is that they'll write code, they'll then try to execute the code. When they execute the code, they'll end up seeing the error messages that you get, and then it goes directly back into the system and say, hey, look, this is what I saw as the output. How should I end up working with this, right? So it's not like you give it a prompt and it gives you back out code. When you use the agentic systems, it's not just giving you back code, it's actually executing the code, looking at the error messages, re-executing the code, changing it, and then doing this in a loop. And that's completely different than using it just as ChatGPT, like, oh, hey, ChatGPT, give me code, because it's actually able to see the error messages that it gets from the code that comes back. And that's really where the difference comes into play, right? So, in fact, this has been kind of highlighted recently. NVIDIA research has actually mentioned that small language models are likely sufficient for the future of agentic AI, because most of the improvements, most of the accuracy actually comes from the agentic loop that you have around it, not necessarily the accuracy of the LLM itself. Having a more accurate LLM does actually help for generating better code the first time, right? But a lot of the agentic systems are actually not as reliant on the accuracy of the LLM for code generation as you would think they are. And there's a lot of research that's basically saying that most of the accuracy is not coming from the LLM, but most of it is actually coming from this feedback loop of the system, right? And so if you've been scared to adopt some of these systems because you've seen the stuff that ChatGPT can spit out, I agree. It can scare the crap out of me. Some things it can hallucinate. But the reason why it's working in the context of code is because it does not have to rely on that first output being correct in order for the system to work, right? And so if you're going to start getting into this LLM coding space, again, I'm going to start talking about the general tools first, and I'm going to talk about a tool that we've been building that kind of destroys them in accuracy. But we need a baseline to understand what we're going to talk about first, right? And the baseline here are basically these three things to start. Right, you have Claude Code, you have Codex CLI, and you have Gemini 3 CLI. If you can try out Claude Code, I would recommend that at this point in time, and it seems to be kind of like a general sentiment, Claude Code seems to be by far and away the most accurate. Now, where these other tools come into play is that Codex CLI is the one that's by OpenAI. So if you already have a ChatGPT subscription, then you can probably already start to use Codex, which is kind of like a nice add-on here. And Gemini, this one, again, if you look at the most recent results, Gemini and Claude are the ones that are definitely on the top. GPT-5 is about 10% less, accurate or some measurement, right? But basically, what it ends up being like is, the Codex one ends up being like, basically a first-year undergrad who just started school versus, like Claude, which actually knows how to write a program that works, right? So Claude and Gemini tend to be the ones that actually work a lot better at least at this given point than the one that you find in Codex. But if you have a ChatGPT subscription, that's one reason to already use Codex because you've already paid for this. And with Gemini, I mean, the reason why Google's been able to get into this game is because if you already have, say, a Google enterprise subscription or something through the university or something, then you might already have a Gemini subscription as well. Whereas Anthropic and Claude seems to be by far and away the best tool for the software engineering right now, but you probably would be paying for this on your own because you're unlikely to have any subscription for it to start. And those subscriptions go from about $20 to $200 a month for pricing. So it could be kind of expensive to use the full Claude Code version, but there is a certain free tier, and I'm going to show you in a second how to get this all going. But just pointing out that there are 3 different ways you can get into agentic AI coding. Definitely Claude Code is the best. Most likely you can get into Gemini 3 pretty easily. I wouldn't recommend Codex, and I have a lot of examples to show that, but that's probably outside of this talk. So before we even get into any of the specialized systems or whatnot, I want to make sure we can get everyone on the same page of what is Claude Code, what does it look like to use it, and how do you get it running? So if you haven't done this yet, right? Now let me switch over to this. So if you haven't gotten Claude Code up and running yet, if you just search for Claude Code, right, it'll come right up in here. Oops. Oh no, that's actually Claude itself. Wait. Oh, is it because I'm already signed in that it won't show me like just the? Well, it's not taking me just to the. Okay, I guess it's because I'm already signed in. That let me just do this in an incognito window then. So if you type in Claude Code. Wait, why is it not showing me the window that I was Claude. Okay, this was coming up at the top of my on the top of my Google before. I'm not sure why it suddenly changed it when I went out on stage here. But so basically, if you type in Claude Code, it's most likely going to bring you right to this page, right? All you have to do is if you're on a Mac system or a Linux system, you copy this in, you throw this into the terminal, and this will get you Claude Code set up, right? Now, what is this beast that you will have just installed? Well, I recommend that when you're first starting to use this, if you're used to doing a lot of programming yourself, what you might want to do as well is you might want to go to your VS Code, you go to extensions, and you type in Claude. What you'll see right here is you'll see that this extension, hit install, and this will put Claude code right inside of your REPL, right? So this now gives me a window right here. I guess it's a little bit weirdly sized. This is now Claude Code running inside of my VS Code, right? So what are the types of things that you can do with Claude Code? Well, As I said, you can. This is a tool for agentic coding, right? So here, let me do something like generate the code for the Lock-Volterra equations in Julia, and write a script that solves them and gives me the plot in phase space, right? So you can do something like this where you'd say, okay, this is something where, again, people here will have said, oh, a normal undergraduate student should be able to run, should know what the Lock-Volterra equations are and be able to solve the equations. Well, then it's well within the space of Claude Code to be able to churn this through. And if I have a script open here, you can see that this is actually tied to my script. So testscript.jl is open on this side. And so it knows that what it's going to do is going to use the prompts here to write into the script over here. And we'll see in a second that it will come up with something. We'll say it's allowed to write here, yes. So I had to give it permission in order to write to a file, but you can see here, using differential equation, using plots. Here's the Lock-Volterra equations. It's almost exactly how I wrote it inside of my notebooks. It's almost like it used my notebooks as training data online. Came up with parameters, right? And so, boom, then you can see that this is viable code right here, right? So this is the basis of Claude Code. If you haven't been using a system like this to help you write code, you should instantly look at this and say, oh, again, I showed you all the installation steps. It takes you about 5 minutes, and you're already right here, right? Now you can start to do something like say, okay, look at the frequency of the oscillations. I know that frequency is spelled wrong, but it doesn't matter. Look at the frequency of the oscillations in the rabbit population. Choose different parameters so that it's very fast, right? So you can start to do things like this, where again, what it's able to do in this context is because it's actually, in this context, it's able to edit your scripts, it's able to run the code, right? So what it's going to do is going to edit the script, it's going to be able to do things like run the code, and then it'll be able to do this to be able to iterate on, well, this time it didn't actually run the code, so I'll just say run the code, look at the plot, and given the plot, double check if your assumptions are correct, right? And so what you can see with this kind of agentic system is that it's not really just the prompting system itself, but it's the prompting system mixed with the tool to be able to run code, right? So first what it did here is said, okay, I'm trying to run this, and I see that differential equations isn't installed. I get an error message when I try to run Julia. I don't have differential equations installed. So what it's then going to do is it's then going to run this, add differential equations. So it's installing the package for me, it's starting to do this system, right? You can start to see the loop in action. So I'll let it run this loop a little bit, and then I'll be able to, while I do the next part here, right? But this is basically one of these agentic systems, right? It's a system that is not just for LLM prompting, but it's a system that is also including the code execution and the reading the results and everything as well. So the first things first, this is what I kind of call step 1 and 2, right? So you set up a system like Claude Code. Again, you could use Gemini CLI or something very similarly, but you set up one of these systems, and the first thing that you want to do is start to do local orchestration inside of VS Code, right? What begins to happen with these systems, though, is that you can start to see that they're actually rather capable at, this one is going to cook for a while to install it. Let me actually cook it for, I'll just say, just use ordinary, or let me add ordinary diffq first, right? So you can already see in here right now that it's like, oh, it tried to do the whole differential equation solver. That's going to take some time. I know that I can make this go faster by making it only use just one part of the ODE solvers. So I'm going to just step in. I'm going to hit escape. I'm going to cut it. I'm going to add the packages for it, and then I'm going to tell it just used ordinary diffq directly rather than differential equations in order to make this run and load faster, right? So I'll do this in a way where I'm going to set up the libraries for it. I'm going to set up its environment, and then I'm going to then put this back in here. It's going to accelerate it, right? So this you can already see that there's a given amount of expert knowledge that is required to be able to use these systems correctly, right? It's going to then switch over to this library, and it goes, oh, with this library, it can run this a bit faster. I'm going to try to run this. Et cetera, et cetera. Oh, but it was doing it in a global environment, so okay, maybe it needs to do it in a different environment, yada, yada, right? But now, well, there's a few things that you start to see with this, right? So again, as this is running, we'll see that it'll be able to kind of improve itself and everything. But there's two things here. One is that you can see I have to give it a lot of permissions. And the other thing is, two, I might want to be doing a lot of these projects at the same time. So again, we'll watch this go all the way through. But while we do this, we need to ruminate. Can we now come up with strategies where we then begin to scale this, where we start to have, say tens of agents all running at the same time, which are doing different parts of our projects and trying to improve different parts of our code, right? Now, one of the issues that you'll see with a lot of these agents is that they can only store so much information inside of their memory, right? And so if they can only have so much information inside their memory, how can we start to orchestrate this where it works out well? Well, the first thing that we need to consider is let's make it so that we break up the projects that such a system is going to work on into very small chunks. And it turns out that we do have a system for doing this already, right? We have systems like GitHub, right? So if you think about what we do with GitHub, right, we basically, so if I go to github/ordinary-diffq, right, what we do with a system like GitHub is we say, here is a ledger of the current code, and what we do is we make pull requests, which are small changes to this code, and then so that way you don't have to understand everything that's going on. You just have to know what's going on with your piece and make small changes, right? This is how a lot of our systems are already working. So if you want to then start to scale up the way that you use these systems, rather than just working on one little part of the project that you're looking at right now, what you want to start to do is you want to start to say, okay, let's make it so that way I have a Git repository that is the source of truth, and let me now have all the agents be pulling from the current Git repository, making pull requests, making small changes at a time, right? And so if you do this, then you don't necessarily need to look at any of the code locally, because again, it will run the code and be able to double check things. Your CI systems will be able to double check the code. At this point, you don't need to even run it at all in VS Code. You just need some way to be able to prompt it and tell it to start working on online, right? So this is where you can start to get to Claude Code CLI, right? So if you do this, you can say, for example, type in Claude here. Actually, let me do this to a sandbox. It's going to be a little bit safer. So I'm going to make dir sandbox, cd sandbox. So this is going to be like not like a true sandbox, but I can make dir test cd test, and I can open up Claude here. And what you see is that you get a whole agentic system here set up, which is a version of Claude that runs in your CLI, and you can then say make the script for the solving the Volterra equations. Or actually, let me come up with something that's a little bit more, just so that way you can see the power right away of this kind of system, right? So let's say I'm looking at this library right here, ordinary-diffq. It has a very small, README. The README doesn't have very many examples. So let me do something like say, in this repository, make a pull request that adds an example for solving the Hodgkin-Huxley equation. Is that a good one? Or yeah, and just give it the pull request, give it the PR, give it right here, right? And this will churn through. Now, there's a few issues that you want to do in order to make this work out. Now, you'll see it in a second, right? The first thing that you have to go is, well, if I was to give this full access to everything that I have on GitHub, that would be pretty scary, right? Because if you're also giving it access to be able to write things, you're giving it access to be able to delete things, right? And so how can you start to do this where this is both effective and able to do a lot of work and safe at the same time, right? So here's a system that I put together that I believe that a lot of people, when you go beyond this piece of running it one piece of code at a time, here's a system that you should be considering as well, right? So if you have some kind of HPC node that you can access often, you can set up this node so that we have you can set this up so that we have a bunch of tmux sessions, right? So is everyone here familiar with tmux? All right, not so many people are familiar with tmux. So if I go here, and so I go back to here, if I SSH over to the system, right? If I SSH over into the system, right? I can, well, I don't have this set up as passwordless SSH on my demo account computer, so I do have to sign in with my phone to verify it. But once I give it access, I'm over in the system. Now, the issue with with working on a remote computer in an SSH is you don't have a persistent terminal, right? But if you use tmux, right? If you use tmux, this gives you a persistent terminal. I can actually then go over and I can SSH again. I can SSH again, just need to right? And if I do tmux ls, you'll be able to see all the windows that I currently have open. So for example, I can get into this window, which is the tmux session. Well, this would be the most recent one. So it'd be the one that was created on January 7th right here. So if I tmux attach -t, this should be session 20, right? If I say hi over here, it should also be saying hi over here because these are exactly the same session. What this means is that I can actually close out of all of these. I can close out of all these windows. I can go back in here. I can SSH back into it. And I'll have to verify it on my phone again. I can SSH back into this, and I can tmux ls, tmux to ls. This window is still there. Even though I closed all the windows for it, I made it so that way it's always running on a remote machine. So even if I turn off my laptop, it is still running. So I can then tmux attach -t20, and I can get right back into that same session. In fact, that session is so persistent that I can do this right here, where I can go on my phone. I can open up a terminal right here, and then I can sign in. Once I sign in, I can tmux attach -t20. I can sign. Oops, I typo. tmux attach t-20, and now from my phone I can say, Claude. So I'm going to run the command. So now I'm going to show you something. So when I'm running this locally, right? If I'm running this locally, you saw I had to keep on giving it permissions, right? And so if you want to start making it so that way your AI agents start to have full reign over what you want, you can start to do things like. I'm just going to show you, right? You can be literally sitting at karaoke, and you can do things like --dangerously, /dangerously. And now if you do this, we need to start talking about things like what's the word? Sandboxing and everything, right? So this is then a sandbox system. Again, this is a system that is now running at MIT that allows for all these persistent sessions. So it's not tied to my laptop. It's not tied to my phone. If I close any of these windows, I can always reopen them back again. But now here I've given it a session where now Claude has set up to be able to do any code changes that it wants on the system, and it won't have to ask me for permissions anymore. And then I'm just going to tell it, for example, take this. And add to the README I don't know what's a nice set of small equations that people like, harmonic oscillator equations. Right. So boom. Now this is something where I can close my computer, I can turn it off, but I still have agents running, making pull requests for me, right? But then the first question you have to be asking is, how can you make this safe, right? One of the ways that I then recommend to make this safe is, so here, let me grab a session here, right? In order for it to be able to have any permissions to be able to push to your libraries, you need to give it explicitly permissions, right? So if you have this set up in a different environment. So here, for example, locally on my own machine, I have GitHub set up, right? Because I'm going to be merging code on my own, and I'm going to be working. But what I can do is on this remote machine. Hold on, I'm not getting the. On my remote machine, I can actually give it a different set of permissions, and let me show you how to do this. Is there rate limiting that's going on with the Wi-Fi here? Because hopefully it's not rate limiting all the yeah. So okay. So then it actually should already have this PR ready. So I'll show you this in a second then. Yeah, so it's going to say the GH auth credential is not set up, right? Because on this remote machine, I'm going to have it sandbox, right? So what is the solution to make this so that way this can be safe? What I found to be the most effective solution is to make yourself a bot account. So you can see here that I have a separate account for GitHub that is only set up. So this is Chris Rackauckas Beep Boop edition. So it is not set up to actually be able to merge any pull requests or anything. It's not allowed to push to master. It's only allowed to read and write in such a way where it can create pull requests. And so I can make this machine be dangerously unsafe, but it still is not allowed to make the final say on any code. I still have to make final say on any code, but you'll see that it's able to make all sorts of pull requests using this system, right? So what I can do then is I can, with GitHub, you can make alternative accounts that you then can switch between two on a single machine. You can set the bot auth to only this account, right? So how do you do this? So let me cut out of here so that way I can just demonstrate this. It's not sending me the auth anymore. Oh, good. I already have another sandbox. So I do GH auth login, right? If you GH auth login, now if you GH auth login on your remote server, the server that you're SSHing into, this will only give that server the permissions here, which it can be separate from your local permissions. And so what I'm going to do is I'm going to ask it for this token, and then you actually if you don't have a text-based browser, what you have to do is you have to take this, you sign in Claude through here, and you take this token here. And then boom, this account, that everything that I'm SSH'd into in that other machine, right? Again, this is in Cambridge, right? So again, the system that is currently running in Cambridge, so at MIT, now has all the authorizations to only act as me through this Claude account, which has the permissions to create pull requests, but doesn't have the permissions to be able to do anything, to actually be able to merge anything, right? Let me just finish the auth here. So congratulations, we're all set. And so now what this means is that on this remote machine, even in this other tmux window, I can tell it to, I just did the GH auth, used GH to make the PR. Well, I guess it actually just made the PR because it just realized I just re-authed. And then, so then I can say, wait 30 minutes for CI to run, and then double check the results. Iterate, and try again. Right? And so you can start to create these bot armies where, again, this one I won't have to look for half an hour. And so while this is running for half an hour, I can move on to the next thing I'm working on. You can start spawning on all sorts of these bots. And what does this actually look like? I can open up this pull request over an ordinary different queue. You can see that it added a harmonic oscillator example to the README. It has the summaries here. And you can see that if it did it right, it should be adding to the README. Here's the LaTeX for the harmonic oscillator. Here's the equations, and here it is right here. This is actually the first second order ODE example, so it looks pretty good. I just double checked it, and boom, let's be reckless here. Now you can see my bot account does not have the permissions to be able to merge this, right? I can jump over to my other account though, and I can jump over to my other account, and I can hit merge right here. There we go. Since it's only to the README, I feel like this is like the right level of reckless, right? But there you go, right? So you can start to see how you can start to increase your speed, right? I just added to the README something that only took like, a minute or so. And again, it's a completely safe form of doing this because I set this up as sandboxes other accounts, and I can immediately spin up new sandboxes just by doing this command where I just keep on going here, and then I keep on spinning off some more sandboxes, and over and over and over, I can have tons and tons of these bot accounts running, right? And so you can actually see the activity of this bot if you're curious about how active it ends up being. In the last few days here, it made 2,000 contributions since August, and I think in the last month it made 273 pull requests, right? So we're talking about something where it's just like a fairly large active environment that is just running by just saying, hey, I'm not going to try to deal with this locally. I'm now just going to give it full permissions to be running on a sandbox, right? Now we actually took this to a next level. So if you go to the sciml.ai, I'm going to show you the latest blog post we put out here. What we did was we started to have a bunch of health bots where we'd say, there's a lot of routine things that you want to do to the code, right? So again, Now, none of these bots are going to be able to say, do your entire project for you, right? If you try to just sell it like, come up with the novel equations for, my climate model and write the paper, it will fail gloriously, right? So what is the right way to start using these kind of bots that exist, given that you know that they only have like the capability of, say, a sophomore undergrad that you've taught on one given topic for, a few months, right? What we've been starting to use them for is to say, okay, we have hundreds of packages that we're trying to do this stuff on, but there's a lot of routine changes that we want to do. So we've ended up creating sub-bots and for a bunch of these different things. They can do things like check the CI health, be able to try to solve an issue. Normally, if it tries to solve an issue, it'll fail, but there's a lot of other things it can do as well. So for example, it can look at parts of your code and try to do a static improvement. It can do things like a performance check. It can do interface checks. So let me actually just pull some of these up in ordinary diffie-q so you can see some of the pull request and get some ideas for how you can be using this yourself, right? So here, for example, you can see here's one that came up recently. What it did was it basically just said, oh, I saw that there's a compat helper request that came up. I'm going to then test locally on my machine. So it spends a few hours checking whether the latest version of a new package that came out is correct. And it actually saw that it needed to do some changes. And so it made the changes to multiple project.tomls in order to make it so that way this version was able to be merged, right? So that's one thing. Version handling is something that's very easy for bots to do. In fact, if you have it set up so that way you tell it where to find information about where breaking changes occurred, dealing with breaking changes is effectively trivialized with this kind of work, right? In order to improve this a bit, actually, let me show you one little detail here. Hold on, let me see if I'm able to auth again. I'm being rate limited by MIT. All right, but okay, if I go here. So one of the ways that you then begin to improve this as well, though, right? So if you go down to CD, you can cd.claude, right? You can then go into vim claude.md. Vim claude.md, right? It turns out that this claude.md file is a context that it gives with every single new agent. And so you can start to tell it all your preferences in here, right? You can start to see some of the preferences that were used to make it so that way this system is more automated. The first thing, some of the things I tell it to do is, you should never force push over other branches, shouldn't force push over main. Again, it doesn't even have the ability to do this on the global repository. So most of the time it's safe, but you just try to make it so that way it never tries to do these things. But some of the things that's very useful to tell it as well is to tell it, when you want to check for CI results, wait for about an hour before checking CI results. So that way it waits for the CI to be completed. This makes it so that way it will make a pull request. It will then wait on its own for an hour. It will check the CI results, and then it will make a code change, and it'll do this autonomously. So some of these bots can run for about 6 to 8 hours, just doing one change, checking whether the change did something, a small change, checking whether the change did something, and it'll just continually run this. And again, as a tmux session, I can then go into this tmux session and see, oh, is this one still running? What is its current state? And you can modify and you can kick it back in the right direction, right? But you can start, if you build out this Claude code, I'm going to share my Claude.md if people are interested in how this is all set up. But once you start to set this up, effectively they begin to run autonomously and use GH to make all of its pull requests. And this is how it knows, oh, I should always use Julia code. I should always use GH. I should wait this long for CI. All this information is embedded with the Claude.md file. Yeah, and so let me then show a few more, another example of this in practice then, right? So here's another one that it was able to do, right? So for example, the static analysis version of the bot, so I'll show you the bots in a second. It spun up a static analysis version of the bot, which said it's going to look at these sub packages, and it started running jet tests on each of them. And I believe in these ones, it found that there was some, most of the jet tests passed right away, and so these ones it didn't make a code change. But in other pull requests, it would actually go and say, "Hey, look, I found some allocations, or I found some trivial type instabilities," and it'll fix the type instability and add the test for this. And so we now have a bunch of these bots that are then spawning on all the different repos and doing things like static analysis checking, doing things like improving performance, improving allocations, and all these things autonomously, right? So then the question is, how do you start to make this autonomous? A lot of this is set up in internal scripts, which I'm not entirely going to share because they have keys embedded with them in them, right? But this is what I then have as this. Well, what you can do is you can start to say, okay, I have, I can then set this all up here where I'm going to go here, and then I'm going to I plan to, by the end of this week, actually sanitize the runner that I have here, so that way it's keyless to be able to run this. Basically, what we should be able to do is I should be able to just say, run, re-enable the SciML agents, let them run any tasks. And now because I have this authenticated with GitHub, right, it's set up for the Claude account, and I have this set up with Claude on here, it should be able to run SciML tasks enable, and it'll enable all 13 of the bots here. I should be able to check this inside of my dashboard, and in a second here, you should actually see it kick off about 20 to 40 agents, which will then start making a bunch of pull requests. And so again, as I'm doing the rest of this talk, hopefully about 30 pull requests or so should be made. And yeah, you can see here that it just did a few direct ones. So in parallel particle swarms, it just kicked off something to try to directly solve an issue. In SciML benchmarks output, it's improving the static analysis. It's doing a CI check now of modeling toolkit neural networks. It basically just took over a whole CI node, a whole HPC node of 128 cores, and now it just spawned a bunch of these jobs according to all the different types in the blog post, right? And in a second here, we'll look at all the pull requests that it's opening up. And so you can see that this is then a very different way to be coding, right? I'm no longer looking at my code saying, oh, is my code fast enough, right? There's just a bunch of agents checking all the different portions of the code. They will find a test snippet and say, okay, I want to see whether this code is as fast as possible. I found allocations in it. Here's the pull request that adds that fixes your allocations and adds a test for it. And you just have hundreds of these just continuously running at the same time. So again, you can start with this just by using VS Code locally, and you can just be using Claude Code directly in your VS Code. But I encourage you to start using the CLI versions and start to build out these systems that is in orchestrating tens of these and hundreds of these running at a time, because you can see that once it starts to scale up, it's able to do quite a bit. So that's just Claude Code on its own. Does anyone have any questions about using Claude Code and orchestrating in such a way like that? Yeah. Oh, yeah.
I don't know if I was first.
Everyone's
Okay. Well, this was an amazing presentation. Thank you, Chris. Well, I want to know how did you build the script to have the CLI tool to control all of the bots in parallel? Did you use Claude to make it?
Yeah.
How did you make it with the shell script or something?
Yeah. So I mean, it started with something like I started writing the first part, but then Claude ended up helping out with the other part. What ends up happening inside of this as well. So let me go into a little bit of the internal agents and internal scripts in parts where I know that it doesn't have keys, right? So I have a few of the scripts that you saw, right? So, well, first of all, I have some things like Claude Skip that it knows that does the dangerously skip permissions. Again, there's a version of this for Codex. There's a version of this for Gemini. So -- YOLO is a thing for Gemini. So it basically knows, these are the special commands that you should be running inside of the SciML agent monitor. Then I started this off, and then what ended up happening was, I ended up building like agent version 1 for CI health check and for a second thing, and then I just said okay, now create a version of the agent for dependency update, create a version of the agent for minimum version. And once it already saw a lot of the different aspects of these scripts, it was able to generalize it quite well. But then the main thing that ended up going on here as well is that it also has a checker that happens every week. So at the end of every week, it looks at all the pull requests that it opened and looks at all the comments that specifically I gave to the bot, and it will then do a pull request to the internal scripts that updates the scripts based off of the things that I've been asking for. So it's been running this for a few months now. This is where it came up with the bot for the It came up with the bot for the performance improvements itself, just because of the number of times like you tell people and like, I can't accept this PR because of performance improvement. It realized that, hey, what I'll do is I'll check a test and I'll just check the performance, and if it has allocations, I'll try to solve those, right? So that all just came from it just iterating on its own previous results from that. So it kind of started with me in there, and I'm actively involved in watching what the bots are doing pretty much every hour, either from my phone or on the computer. But I'm pushing it in the right direction so that way it doesn't go off the rails, but it's also autonomously helping and fixing itself. So it's a bit of both, yeah. But that's also why I want to make sure that before I show all the scripts, because I know that it has some SSH keys and such in there, so that's why hasn't been made public.
Yeah, I also have a question. So, what's your thought about the cost of this compared to the value? I know right now the prices of tokens is quite cheap, but there's also some cost associated, and also if the tokens are priced more according to the energy consumption, and also about the cost in terms of electricity and to the environment. I mean, how do you see the trade-off between the value and the cost?
Yeah, that's a good question, right? Because I mean, yes, by kicking off 20 agents right here, what I did just during this talk, right? Probably is using the electricity of at least, like 200 normal people, right? So there's an environmental cost that you should be considering with this. It does give you a lot of productivity. Now, I talk about this a lot in some blog posts. I'd say check out the recent blog posts on a stochastic lifestyle. You might have read these on Hacker News and stuff. This one went around quite a bit. But these two blog posts, Claude Code sucks, but it's still useful, and a guide to Gen AI for expert programmers, right? One of the things that I talk about with these systems is that they can get really stuck really fast. So think about it as, if you're mentoring some students, one of the things that you'll see is that there are projects which the students can do, and sometimes the student is just incapable of doing the project. If the student is incapable of doing the project, sometimes trying to train them on that project just doesn't work. You just put them to a different project, right? And the same thing will happen with these agents, right? They'll open up some pull requests. In fact, the one I can think of one from yesterday. It was on Rencho's library. Which one? btrees.jl. No, let me look in SIMO. So what you'll find is there'll be all these different cases that come up of rooted trees.jl. That's the name of it. So for example, it is able to be pretty effective in some cases. So for example, when I was adding static analysis tests, it was able to find out, okay, I could figure out, here's how I add jet to these different tests, yada, yada, and it was able to do this quite well. But we really just kind of work on this space of, if it starts to go into a loop and starts to do things wrong, you don't even try, right? So here it created a pull request that tried to add 3 new features. It did not get these features perfectly correct. It got them about 90% correct, but it wasn't able to respond to the comments fairly well. So you can see over the span of 2 days, it was trying a bunch of different things in the code. So it probably used, a decent amount of power to be able to run this. But at the end of the day, we saw, hey, it wasn't able to do this. It started disabling tests. This is actually a behavior that you'll start to notice. If it starts to do this thing where it's like, okay, run back and forth, and it's not able to figure something out, the moment it starts to disable the test, just click close on the pull request. Don't even try to use it anymore. So you might think about that as that was wasted work, but in terms of human time, that was no more than a minute or two. So in terms of human time, it was no more than a minute or two. I let it just keep on running. I saw it started deleting tests. That's the moment I just say, I'm not even going to look at what it wrote. And so in terms of human time, it's very quick to make this very productive. But the downside is you are using a ton of power. I mean, again, there's an entire HPC node that's only running this bot, and it spent 2 days on, so 2 of its 128 cores was just on complete junk that we threw out. So there is an environmental cost to this, but you can see that there was 175 pull requests that did merge, right? And so there's about 175 that didn't merge, right? So we have about 50% of them just complete junk energy, but the other half works out pretty well. And if you make it so that way, you just say, have some keys where you just say, when this is junk, I'm not even going to waste my time with it. Then you can be rather productive, even if it is somewhat unproductive energy wise. Now, is that good for the environment? I think that there's a lot of discussions to be had here, which are, the environmental and social impacts of this are a different discussion than the technical. How do you do this and how do you make it productive? And I think that we do need to talk about the environmental and social things there. But at least with the prices that they're at right now, they're being subsidized heavily by VCs. Use this and make your repos really good right now, and we'll figure out the other stuff later.
For the pull requests that get stuck or that don't really work out, and I'm hesitating to copy your setup that directly makes pull requests. I feel like I would want to review it first before putting it out and notifying all the other contributors. do you have any ideas for such a setup?
You could make it so that way it makes pull requests to your own fork of the library, and then you pull requests from that. That's one way to make it so that way it's a little bit safer. Because SciML in general, I have BDFL of SciML. I'm happy just to throw this out there. But yes, when I do things outside of SciML, I don't make it just put a pull request out. And I do a pull request to my own fork, and then I manually open up the pull request from there after I double check the code. But you can see here, like this is a pull request that was just opened 3 minutes ago. It's fixing package compatibility by removing test.project.toml. So it found that actually this library had a test project.toml, even though we normally run things without the test project.toml. This is probably one that we can merge right away. We'll wait for the CI test to run. It'll iterate on its own. I can check the agent, but it was probably going to wait the half an hour here. Going to wait for the test to run and iterate. And so this is probably something that's quick to merge, right? But then there's some that we'll delete right away. And if it's not a repo that you own, in terms of everyone here in the community, don't set your bots on other people's repos because it will create a lot of junk. Again, 50% of it's junk, but it's okay in your own repo to just be junking half of them, right?
And one more question, like I'm using Claude, the agent, but via Copilot because that's what I have a subscription for. Do you have any experience with that, like Copilot CLI?
Yeah, so the Copilot CLI, the thing with the Copilot CLI, though, is that you generally don't get the latest Claude agent without having also the Claude subscription. The difference between Claude Opus 4.5 and the Claude Opus 3 or whatnot is gigantic. So I definitely would say cutting out cutting out the extra subscription, going straight to Claude and getting the actual better model does a bit better. And again, it's fine to do a lot of this locally, but if you're going to scale this to running a lot of agents, you want to pull this away from local and you want to get a persistent session, because a lot of these sessions, again, when I'm saying like, oh, this thing needs to run for 8 hours, if you have it running on your computer, that means you can't turn off your computer for 8 hours, right? So if you set it up so that way you have a persistent session on a remote machine and you tmux to it, then you can, from your phone or from your computer, you log in, you check it, you give it a nudge, and then you do this. And once you start getting to that level, I think that you probably don't want the GitHub Copilot one. I would just drop all those just because it's easier just to orchestrate it through the CLI agents. But maybe that's just a personal thing. But I mean, I showed you my setup here. Within 5 minutes, you can get something similar to set up to this. So again, so I would recommend doing this if you have like a remote machine that you can SSH into that has sufficient power. This is a really decent system. The other thing that's nice about this is that it also sandboxes it, right? Because if you give it dangerously skip permissions, it could delete everything on your machine. The worst that happens is it deletes everything on that machine in C-cell, and we just have to wipe the machine and start over again. We only have to wipe it every few months or so it's okay. If I had to wipe my laptop, that would be a very different story, though. Yeah.
Thanks, Chris. Nice presentation. Given that you used Claude and enabled dangerously, could you maybe explain to the rest, maybe in a few minutes, what prompt injection is and how it can steal your credit card information? For responsibility's sake, right?
Yeah, I mean, so I mean, with the prompt injection, I mean, like when you do dangerously skip permissions, it has access to everything on the computer, right? And it will run, and it'll be able to run code on your computer. It could do things like delete your operating system because you're giving it full access. And when you say dangerously skip permissions, it doesn't have to ask for permissions to do anything, right? I think that the way to then do this effectively is you just have to sandbox it, right? So you have to be running that Claude agent inside of a sandbox where all of the information that it has access to is only stuff that you want it to be able to run with, right? So, for example, on the agent on the machine that is SSH'd into that I run the agent, it does not have access to any of my personal information. Like it's just like it's a Linux box that has only Claude installed, only Julia installed, and the only GitHub authentication that it has is to the Claude agent bot, right? And so it will make some weird pull requests every once in a while, right? But it doesn't have enough information to be able to throw everything like that. But this is also why I'm saying if you're going to use the dangerously skip permissions and stuff, either be running this inside a Docker container or do this non-locally, because you don't want to do any of that locally. Because yes, otherwise it would have in your computer all of your credit card information, and it could make a pull request that puts all that in there, right? So again, I think that the main answer to a lot of this is sandbox appropriately, and the easiest sandbox is just to have a completely different machine that has permissions and access to nothing. Yep.
So I like Mistral AI, and they have Mistral code. I'm wondering why it was not in the list of your comparison. Was it just lack of time, or is there something there that would be missing?
Lack of time. I mean, well, Mistral is mostly an orchestrator over other models, right? I was just basically pointing people to the three main models that, Mistral, I believe, uses a lot of the Anthropic models by default, right? Yeah, so I found it more effective to just go straight to the Anthropic models. I mean, because I don't think it's so difficult to build your own orchestration on them. But people are like in Mistral and things like Cursor, and things like this. So if you're more comfortable, if you're familiar with those, it's totally fine. I kind of just tell people I think sooner or later, if you want to be doing more than just working locally, right? Using the CLI, just doing it all through SSH and command line gets you up to scale really quickly, and I would just cut everything else out. But again, that's maybe a personal thing. But I showed you the setup here, so it's difficult for me to see how someone else can get you more customizable thing in like the 5 minutes it takes to set this up. So, but to each their own.
Thanks.
So I do want to, we'll take the last question here, and then I want to get to the last part of the talk here.
Hey, Chris,
Yep.
I'm wondering, for you and for a lot of people, you have a lot of experience. You know how to discern what is correct and what is not correct, and even though you're gating the changes with pull requests, I'm wondering what are your thoughts on people who are just starting out with coding and being confronted with these agentic tools right away. I'm concerned that people that have no experience and start using this will never get to reach the experience that you have and a lot of the other senior people have, and that way they will not be able to discern what is correct and what is not correct, and we will reach a point where all new people that start coding in the next generation of programmers will never be mature enough because they offload all their thinking and all their responsibility to these models.
Yeah, it is a good question. It is a good question. I mean, because when you start to see this workflow, right? The thing that I would kind of start to say is this workflow is not necessarily new, right? This idea of here's a workflow where I just showed up and here's a pull request where it changed to formatting to Runic. Here's a pull request where it changed package compatibility. And in fact, if I had my email open, you would have seen that it just created like 30 pull requests. And what I would do is I just go through pull request after pull request, looking at the code change, saying change this and whatnot, right? And while that might look to many people like a new workflow, it isn't a new workflow, right? Because there are a lot of people who have been doing that workflow for many decades. That's your professor, and that is the senior dev of a software company, right? And so normally, if your professor is not writing their own code all the time, I mean, people in here tend to be writing code, right? But a lot of professors, right? You have a lab of 16 people, and your students come in every morning. You look at their code, and as the expert, what you do is you don't necessarily write on their code. You look at their code and you just say, that's wrong, that's wrong, that's wrong, come back tomorrow and fix it, right? That's exactly the same workflow as this. Now with it, for me to be able to say, instead of paying for 16 grad students, I now have 16 grad students, but I also have 48 of these agents that will respond to me at midnight, right? And so it isn't a new workflow. It's just saying we're now giving the ability for everybody to have their own grad students, right? And then the question really comes into play is this a good thing for learning, right? So if you already learned how to do all this, I think you naturally progress into this type of field where you say, okay, I've written so many differential equations that when a PhD student comes to me and they say, hey, look, I have this ODE and it's running slow, I know the first 20 things to look at, and I just look at their code. It only takes me like 5 seconds, and I'll be like, okay, you wrote it out of place instead of in place, and you should do that. Like I've seen this thing so many times that this is why code review is so easy, right? And so this kind of workflow is set up where it's just say, if you've gotten to the point where you're good at doing code review and you can do it quick, swiftly, and accurately, and safely, the main thing is safely, right? Because you have to be able to know, when am I doing code review in a way that is fast, but if I know if I made a mistake, I'm okay. I'm like, okay, I'm looking for this kind of test and everything, and that comes from a lot of experience doing this, right? If you've gotten to the point where you're very good with code review, this is an accelerator to that. Now, if you're someone who's still writing code themselves, should you make the jump to be doing only this code review style? I think that there's a major question there in pedagogy that's coming up. I do think that to a certain extent, you need to write a lot of code yourself in order to get the feel for how code works. But I also think that this style, I don't think that just writing code actually teaches you how to work through code review. I think that a lot of people, when you first become a professor or senior dev, you instantly hit this, right? Because you work, in the first, for your 5 years of your PhD, the first 4 years of your postdoc and whatnot, you spend the first decade of your scientific life only working by yourself. And then a lot of people have a really bad time transitioning to this. Oh, now I tell a student what to do. How do I work through prompting a student in order to make this work? How do I work through code review? Is actually a completely different skill. In fact, a lot of scientists never really adopt it and tend to be individual contributors rather than ones that run organizations, right? And so I kind of think that with the way that things are evolving here is that, again, these agents are not the smartest thing in the world. And so I think that there still will be the path for people who are very good independent contributors that'll be able to beat it on doing things like writing really fast code or writing code that is very specific, writing code that is able to handle, certain floating point aspects directly. In fact, you can see right now that if I could pull up a pull request, it's like, okay, what is the type of pull request that I would still work on that the agent wouldn't work on, right? I think that this one right here is exactly the type, fixing t-stop overshoot for event dense time triggers. What's going on in this pull request, right, for example, is you have this property that 0.1 plus 0.1 plus 0.1 minus 0.3 is not equal to 0. So if you're stepping by delta t on a number that is not divisible by 2, then you can end up not hitting the points that you said you would directly. And it turns out that AI agents are not able to handle these kinds of numerical analysis issues very well, right? And so I'd say, if there's still a room for people who are experts in numerical analysis to be able to handle these kinds of issues, experts in doing things like code performance, et cetera, et cetera. And so there's still a lot of room for individual contributors. I would say that if you're a student right now, I would very well specialize in writing code for a specific kind of issue while learning to also orchestrate and work through code review. And I do think that this code review style might be something that is brought into undergraduate courses more. I've actually been talking with some folks at MIT even about, okay, the first programming course, should you actually start programming by doing some prompting and showing them, okay, here's what the prompt came up with. Now this is what the code looks like. And this is what the pieces of the code mean. Here's how I should change the code given what I see, right? Bringing prompting into the very first programming course. I wonder if it's going to work or not. I don't know. This at least helps out senior devs a lot. How it's going to do to pedagogy is very, very unclear at this point. Hopefully.
How you reach the senior dev, that's the issue, right?
Yeah, which again, I mean, some of it comes from writing some code yourself. But again, if you just write code only yourself, you will never get to that level of, oh, now I feel comfortable with code review. You kind of have to do code review in order to become comfortable with code review. And so it's a different skill. So do you start with that or do you not is a very good question that I don't think anyone has ever had to answer before. But yeah. I think you do have to learn both at the same time, and so I think that we will completely change the pedagogy for programming. I don't think that these I don't think you can keep these tools out of the undergrad programming course. They can do your entire homework for the first year. They could do your entire homework for the second year, right? The students will be using this, right? And I think that we just had to redesign all the courses around the idea the students will use this as a shortcut. So how do we make sure that they're still learning something effective? And how do we make it so that way they are more competent in the era for which this is a standard way to do things?
Yeah, you need to make sure that they actually learn
Mm-hmm.
as opposed to just offload their thinking, right?
Yeah. And I'll get to that a bit in the next part here. So this is just the standard tools, right? So if you haven't seen these tools yet and you're like, oh, what do you mean standard tools? These are the standard tools. Everyone here can start to download and start to use this today. In fact, by the end of the day, I encourage you, download Claude Code, start using this, start asking your questions. By the end of JuliaEO, everyone should be using some form of this just to double the number of pull requests you're making each day, right? But now the next thing is how can we actually improve on these things, right? So this is just like the baseline. All right, so this is what I'm saying. This is just your daily, like, okay, it's just checking your code, improving your code, yada, yada. But now as modelers, I've been mentioning over and over that this thing is not smart, right? So how do we make this thing better in the space where we also know that, making a $1 trillion training run, a $10 trillion training run is not actually going to be the true answer, right? It turns out that there's some fundamental things we need to think about for improving the accuracy of agentic AI for engineering and modeling, right? So when we think about how this system works, what we can see that makes this system work out well is that it's really the agentic loop that makes it work, right? It's not the accuracy at which it writes code is helpful, but what really makes this thing work is the fact that after it writes the code, it executes the code, it reads the error messages that it got and tries to fix the code and write some more code, right? It's this loop to it that makes it so that way it works better. So then the question that we really had was, can we make it so that way this loop understands more about physics, understands more about computational science, and it requires less from the agent to be able to actually get right? This is, if we can make it so that way it can understand more about what makes equations correct, if it could get more error messages from it, then it'll be able to correct itself a lot more. That's like the general hypothesis here, right? And again, it's kind of matching this idea of the NVIDIA research to say maybe small language models are sufficient. So let's assume that the large language models are not getting any better. In that assumption, how can we get more accuracy out of these systems, right? And this is what we then started to build out as Dyad, right? And the key thing here with Dyad is we started to say, okay, let's build a language that works in a specific way, right? So as a language, it is a statically checkable language where all of the equations in the language have units, and so therefore you can check for things like unit compatibility on any equation, right? Nice thing about that then too is that if you ever write an equation for which the units are incorrect, the compiler at a static check time can give you a statement that says this is a physically impossible type of equation, right? And so it can use that to be able to iterate and say, hey, look, I wrote the equation that I wrote down is incorrect. And so the difference here also is that here what I'm writing is like, dir of x equals y, right? All I'm writing is symbolic equations at the very top level. And what we'll use a symbolic engine to be able to generate what the code is directly from the physics. And so that step of, did I create the right code for the model that I wrote down, is a completely automated, right? If we do it like this, then the actual agent, the LLM, only has to get correct the high-level symbolic representation of the model. The code that is generated, the way that it's executed, the way that it's parallelized, all of that being done through the compiler means that there's a lot less that can go wrong for the system, and it gets better error messages because the only things that it's allowed to write down are things for which can be unit checked and can be checked for real compatibility. And this is what we've been developing as the Dyad modeling language, right? So it's a separate language from Julia, but it's a language only for modeling and simulation that then all that you can do, you can write down symbolic equations, and it will then compile by generating the Julia code for you, and then generating the differential equation code and running that. And so this is what we're calling the Dyad system. Again, I'm running a bit short on time here, so I want to get right to the final piece here, so you can get the wow. But it's a system that is both has a graphical user interface, so it's like something like Simulink or Magdalka if you used these tools before. It both has a graphical user interface and it has a representation as code. So it's a one-to-one representation, and all the code is then related to just the equations of the model. The rest of everything else, like how do you turn these equations into runnable executable types of solvers, is all going through a symbolic system, actually the modeling toolkit equation system. And then one of the nice things as well is that at the very highest level, it doesn't need to guess what a lot of these models are, because it's a system that is able to take components from other models and be able to compose them. So you can say, hey, I have an RLC circuit, or I have a resistor, a capacitor, and I have all these other things. Connect all these together and create the code that is related to these systems together. And it's able to then use pre-built differential equations and compose them together. So as a modeling system, Dyad is a modeling language that has model libraries and a system for being able to say, make a connection between a quad rotor and a model of heat. And then when it's able to then build you and give you automatically the differential equations for the composition, right? Now, the thing that's done there is the composition process is all symbolic. It relies nothing on the large language models, and so you can be guaranteed that when you compose things, you're getting the correct equations, right? So then the only thing that needs to be done is tell me what models to do, create new components create new equations, and connect between existing models. And then we also give it a bunch of existing models, things like electrical components, so like resistors, capacitors, valves, pipes, clutches, gears, all these things that you would actually have in realistic scenarios, along with fully realistic models of HVAC systems, including two-phase flows for refrigerants and battery systems, including all the the electrochemistry of lithium-ion batteries, nickel-cadmium batteries, and everything. So that way you can start to do things like say, hey, give me a complete electrical vehicle with a lithium-ion battery and with a drive shaft that matches a Chevy Volt, and then it's able to construct that system for you using all these different pieces, where it's then able to pull from pre-built libraries and components, right? And so, I want to kind of get to the bang here at the very end, which is so this system ends up being fairly powerful and being able to get pretty correct at building models. We, in fact, are trusting it enough that we run live stream sessions on YouTube and Twitch where we ask the general audience to give us questions for models, and people just tell us, build a model of a Chevy Volt, right? And we just do it live using the agent fully. And so I recommend if you're curious about this, come to one of our Friday sessions. They're very fun. But I will show you what this kind of looks like with a quick video that we made of Dyad in action. And then I'll show you, and I'll start running the Dyad agentic system while we're doing question and answering at the end here. But
friction brake system.
But I think that it's not routing my sound. Maybe should I just do the? All right, we'll do this lo-fi style. What? No.
Model using an agentic workflow with Dyad. When the driver presses the brake pedal, the braking system applies a force, causing the brake pads to clamp onto a spinning disc or drum, thus creating friction that resists the wheel's rotation and can bring the vehicle to a stop. This friction creates heat that causes the brake pads and disc to warm up. Engineering a brake system requires meeting both mechanical and thermal requirements for safe vehicle operation. Utilizing a modern workflow to engineer this system requires physical models of the friction brake in the vehicle. Here we will develop system models that are typical of the ones required for model-based systems engineering. But we will do so using an AI agent, basically by posing the problem that we want to solve and ultimately ending up with models that execute and predict the mechanical and thermal dynamics of the system. Agentic workflows are fundamentally altering the way that the human and computer interface works, leading to the potential for massive gains in engineering productivity and efficiency. These agentic workflows are a core part of our Dyad product and will be demonstrated in this short video. We start by asking the agent to help us create a model for the friction brake that can capture the relevant physical interactions. The agent then does research and provides a mathematical formulation that meets our specification. This step alone is massively helpful. With just one simple query, you potentially have a model that can be implemented immediately, along with reasonable parameter values that are representative of our application. We can even easily iterate on the model by asking the agent to refine the formulation. As you can see from the responses, the agent plans and then returns with a new formulation, including nicely summarizing the changes requested. These changes can be as complex as asking for different mathematical formulations for the physics, or as simple as changing the interface for the model. Once we are happy with the formulation, we ask the agent to implement the model for us in Dyad. The agent knows which component primitives are available and utilizes them to implement the model. Now we have executable, fully parameterized code that represents the physics. Note that the code is well documented and very nicely formatted. We also ask the agent to create a unit test that exercises the model under specified boundary conditions. We can test that the component is behaving correctly and also subsequently use these tests to help refine the formulation and model parameterization. This agent is not just capable of generating the model code, but is also contextually aware of the models we are creating, the relevant physics and expected responses, and also key numerical considerations. We now have one part of the model that takes a brake command and generates the resulting friction torque and heat based on the vehicle boundary conditions. Because we are also planning to work with the model moving forward in a graphical interface, we can add an icon to the model. This icon will also appear later in the video when we use this brake component in the full system model. We can go through the exact same process to develop the thermal model for the brake. This part of the model will provide the thermal dynamics of the brake system. We start by asking the agent to help us create a thermal model for the brake system that captures the relevant thermal interactions. Again, we go through several iterations on the model formulation, model interface, and model parameterization. Note that the agent is also reasoning regarding our proposed formulation changes. It even provides us information back regarding how these changes will impact the thermal dynamics in different temperature regimes, so that we can evaluate whether these changes are appropriate for our modeling needs. After we ask the agent to implement the final model formulation, we again ask for a test case to help validate the model. Note the really interesting interaction with the agent. The agent knows how much heat is put into the system in the test, and notes that the heat in the model does not balance, a sign that there is potentially an issue with the energy balance in the model. The agent then performs an energy analysis by looking at the individual terms in the equations. The agent rightly concludes that the system has not run to steady state, and thus should be run longer and proceeds to do so. This is completely unprompted, high-level thinking by the agent, providing insights that can help even experienced engineers rapidly develop and validate models. Now that we have a model created by the agent to our specifications, we also want to visually see the components and how they are connected. There are no graphical annotations associated with this model as generated by the agent, but we can ask the tool to render the diagram and automatically lay out the components. This graphical information is now part of the model, thus ensuring that the model can easily be used and modified in graphical form moving forward. We now have a second part of the model with a compatible interface to the brake that captures the essential thermal dynamics of the brake system. Again, this component is flexible and fully parameterized for ongoing usage. The last part of the model is a representation of the vehicle. Again, we start by asking for a simple vehicle model that will match the interfaces from our brake and brake thermal models. Because there are so many different ways to model vehicles, we provide some additional details on the sort of model that would work for our current needs. We can then change the parameterization and create a test case. There is a really nice interaction with the agent here. We provide a very high-level engineering query to set up a particular kind of test that is used to calibrate the representation of the vehicle load in our model. Note that we don't provide any additional details other than run a particular test and propose values that represent a typical vehicle based on the results. The agent then researches the test, figures out how to implement it in Dyad, and then runs the test trying different parameter values until it finds values that match a typical vehicle response. We also get nice summaries of the runs and the plots showing the various responses. The agent even updates the model with the calibrated parameter value. That's a huge amount of work that has been completely automated by the agent. Now that we have developed the individual components of our system model, we assembled the entire model that would be used to conduct virtual experiments for the brake system. We used the auto layout capability to generate the graphics for the model. Here we see the icons that we added to the individual component models. But this auto layout is not just a static layout. It represents the starting point for the engineer to continue working with the model graphically. Here you can see that this diagram is live. The components can be moved around the modeling canvas and the connections can be deleted, created, and modified. The system model, which was created entirely by the agent based on high-level queries from the engineer, is now fully implemented from reusable parameterized components and is fully graphical and ready to use in Dyad for ongoing development and experimentation. Depending on the experience level of the engineer and also their familiarity with the modeling tools, this entire modeling process could easily take a day or even more to accomplish, but here we have our answer in a matter of minutes. The future of engineering tools is here, and it leverages AI as an integral part of the engineering workflow. Contact us at sales@juliahub.com if you have any questions or would like to try these tools.
So yeah, if you've been writing all your ODEs yourself still, that should probably excite you, but also scare you. But yeah, I mean, I'll take a bunch of questions, and again, I think that I kind of went over in the first part, so I didn't have enough time to kind of show you how running Dyad myself here to be able to show you that these are not pre-canned videos. Again, we do this as a live stream now, so I'd love to just take a question from the audience here and just have it generate the code and everything. We'd be pretty surprised at what kind of models it comes up with. So does anyone have well, I guess let's just do something like create a basic energy balance model, EBM, of the Earth. All right. Yeah, because if people want to start playing with this and everything, we can start to see if we create a basic energy balance model, it's going to have to do a bunch of iterations to make sure it gets the right equations and everything. And you guys, we can get some feedback from the audience who will say, add this to the model, add this to the model, and you'll see within 2 hours how much of a climate model we can end up with. And it's kind of a fun exercise. So again, if you haven't been using these kind of agentic tools for coding yet, you should be, again, both scared and excited, right? This is a very different way to be doing coding. If you haven't been using AI machine learning in your coding yet, hopefully you start to use something like Cloud Code, or if you do a lot of things where you're doing a lot of modeling and simulation, you can check out Dyad. We can help you get it up and installed and running. Again, because it has all this special, static analysis and everything in the context of creating differential equations, it ends up being a lot more accurate than Cloud Code. We have a paper coming out next week that quantifies this. But we'll be happy to get you up and running with any of these tools, because we think that the whole Julia community should at least adopt them to some extent. So thank you.
Do we have to have questions at all? Or? Yeah. Okay. I kind of just wanted to get back to this denial question I asked before, and maybe add a layer to it, which is essentially what you demonstrated, right? I could imagine somebody having the same presentation, but towards writing papers and reviewing them, or writing, say, NSF proposals and reviewing them. Do you want to discuss this a bit? Or
I'll tell you right now that I have the agents set up on my Overleaf and a bunch of GitHub accounts, and I would give them prompts like, so for example, one of the really nice things to use them for is if you have a database of a lot of grant proposals that were not accepted, right? Again, 15% of grant proposals are accepted or whatnot. If you have this whole backlog of different things, I had Alan send me an email that said, oh hey, look, MIT needs an internal, they sent around some internal thing, I forget exactly what it was like forward or something. It's only like $300,000, so let's put together a grant request for this by the end of the week, right? I didn't want to spend time on it, so I just sent a prompt to it that just say, take a look at one of the grants that were not accepted before, make a 3-page version of one of the NSF ones and send it off, right? And it wrote it, and I didn't spend more than 2 minutes to send it over to Alan. Alan was like, oh, that looks good, so it got an independent check. I didn't tell him afterwards that it was completely prompted, but and then so we put out the grant. So again, grants that we wouldn't have applied to before because it would have been too much work. If it's only 2 minutes to regenerate it from a different grant we already had, just do it. So we're using this to slam out a lot more grant applications, and I assume that everyone else is doing this too. You might as well just, if it's that much work, you might as well just apply to 10 times as many grants. And so if you're not using this, if you're still writing it by hand, then we're going to be flooding. That's part of the plan, and I assume that everyone else is going to be doing this too. For papers, I think it's a bit more difficult with papers because it's very difficult for them to write things that have any sense of novelty to them. And so it's very good for them. I mean, I think take a 20, 30 page NSF grant and turn it into a 3-page internal grant for like a lot less money, right? I think that's exactly the place where they work out really well. If you try to ask it, write a new novel grant, for that's 20, it's just going to basically spit out things that's, people have already done. So it really kind of requires that you create a lot of source material for it. I mean, and you can see that with Dyad as well, right? We create a lot of source material. If we create, vehicle models, we create multi-body models and all these things, and it's able to compose it. It's able to say, okay, I can take a friction brake and I can take this, I could stick them together, right? It could summarize and it could stick things together, but it's not really good at creating new things. And if you kind of keep it within that mindset, then you go, okay, what I'm going to use it for when generating code is I'm going to use it to tell it to create new tests for me. I'm going to use it to improve the performance of my code, but I'm not going to have it try to create a new ODE solver. It'll fail every single time. For my grants, I'm going to have it, if I have something in NSF form and I need that grant in NIH form, converting it, perfectly fine. Converting it and turning in for a Simon's grant, perfectly fine. Writing a new grant based off of something, terrible. And so it tends to see that it doesn't do so well with writing papers because by definition those should be new. But taking that paper and then making it, summarizing that as one paragraph as part of a grant, and then and then writing the next paragraph for how what your grant aim is for your next part of this will be. That's perfectly a good use case for it, right? So I think the key to all this I think is they are not good for everything. They're good for some things, and using them effectively is the way to make them productive.
To the extent that it's not like a trade secret, can you talk a little bit about what level of work needs to go into making something like Dyad? Like, is it just kind of open source tools with the first kind of thing that you would think with, like Reg or something like that, or do you need to put a lot more work in to make it actually?
There's a lot more to it, and if Vinas didn't get sick, he would have been here at this to be able to talk a lot more detail into the agent orchestration that he's been building here. I think that there's a lot of what goes on here is this making it so that way it knows what to read, and a lot of prompts around, okay, if you see these kinds of error messages, and then start to look into this, and so it has this like entire workflow of tools where it starts to say like, oh, I can diagnose that this is a numerical stability issue. Okay, if it's a numerical stability issue, what should I start looking at? Okay, I should take the solver, I should put it into this different mode. And basically what we've done is we've encoded the way that, a lot of our expert modelers actually looks at how do they fix their equations. And we've turned that into, this is how people do it. So do all these steps. And so we basically, every single time we have new models that people are debugging, we're just capturing that as new prompts and new setups, and then we have our own agent orchestration for this. So this actually, what we're doing with Dyad still uses the Anthropic models, but it has a very different system for how it's using this information. You can actually see a little bit about this as well. I mean, so for example, in ordinary diffie-q, we have we have a pull request that hasn't merged yet, which is on the if you can kind of see the kind of stuff that's going on that's like helpful towards Dyad. We have a new logging system that's coming out. Again, there's some things going on with the pull request, et cetera, et cetera. But so, for example, one of the things that we did is we said, okay, the agent needs to have a lot more information about how the ODE, why an ODE is failing. So we end up creating this new verbosity system where, let me see if there's a good page for, inside of core here, verbosity, right? So I'm creating this new verbosity system where it has all these different modes. So in the standard mode, what it does is it doesn't tell you about what happens with the linear system. It doesn't tell you about the nonlinear system, all these like extra little details. But there's all these new switches inside of there for it to be able to say, okay, for every single step, tell me what the error estimator of the step predictor was saying. Tell me what the condition number of the Jacobian is. And so you can make it so that way it prints basically like an entire gigabyte of information for every single ODE solve. And then we're basically teaching it how to read all this information to learn, okay, if you see this kind of information, this means you have a singular Jacobian. This means you have, the type of behavior that would come from a DAE that's changing index. The way that you would fix this is this. And if you see this kind of behavior, so if you see steps failing, but you have high EST, then what you have is you have a numerical instability inside of the linear solver. So change the linear solver from an LU factorization to an SVT factorization. And so we're just building up this bit of knowledge that's just every single thing that we know about numerical analysis with how do you query the ODE solver for more information for how to be able to capture this. And, with a team working on this, for the last, few years and whatnot, we're able to build quite a bit of information in there. In fact, at this point, I don't even like to debug ODEs myself. If you give me ODEs, I like to use the Dyad engine. And when the Dyad engine goes wrong, I like to improve the Dyad. I tell it more things to look for and then, basically just kind of do that instead. So we're basically just trying to say, instead of trying to solve anything ourselves, let's just keep on improving the agent's ability to debug. And if you do that with a big enough crew, it starts to outperform what most people are able to do. And so there's that aspect of it, plus the language aspect of it is a huge thing, right? It's a language-built like modeling toolkit, but it has more static analysis capabilities. And having the static analysis capabilities makes it so that way it's much better at being able to catch errors early and often, and that makes the iteration process much smoother. So I think, it kind of is like these two things together of it knowing a lot about numerical analysis, plus it having a lot of constraints on what is an acceptable model, right? Models have to have the right units, everything has to be connected together, et cetera, et cetera. Those constraints in what you're allowed to write really improves the agent accuracy a ton. And so we're just kind of, again, it's still kind of early in this process, but we're really kind of spinning up more and more people in that team. We're getting, a lot more of this information from a lot of, how a lot of, industrial users and, building airplanes and everything, how they're using this, iterating on the tools around that. And it's at a certain point, I think that it's less about it's less about, what is like the proprietary, like what is the agentic system looking like. I showed you a lot of my open source one that I use in SciML, right? But it's more about what is the information that's baked into there, about what it knows about debugging ODEs, what it knows about, the physics of equations, what it knows about, HVAC systems and vehicle models and all that. That can be, that is the proprietary information I think is much more difficult to kind of put back together. So yeah, very good question. And yeah, while this is running, right, so while we were talking, it created an energy balance model, but then it realized that it didn't get to something that was a realistic model, so it actually asked if it wanted me to add something to it, and so it added the greenhouse effect. So let me actually take a look here where we are with our energy balance model. So our energy balance model here, so we have a temperature, we have incoming thermal power, we have outgoing thermal power, we have the solar constant, we have Stefan Boltzmann constant, we have the Earth's albedo, which is just one piece here. So as someone who's done things like these kinds of albedo models before, I'm saying, we could probably do this with different latitudes or whatnot. But okay, but then it was able to come up with, we use Stefan Boltzmann law plus incoming solar radiation. That's a very basic energy balance model, and we can continue to prompt the agent to improve this as well, right? So you can see that it's already starting to get on its way to an EBM, but there's still a lot more to do. So I'd say let's make it a paleo climate model, include some of the corrections from the Butico model, Butico Sellers model, right? And we'll see if it can figure this out. So actually, the first research project I ever did was in paleoclimatology. So that's why I know about EBMs. But yeah, let's take the next question.
Yeah. So I'm definitely not an expert on this field of modeling and all of these equations and all of these systems. I'm out of my comfort zone here, way out of my comfort zone. But I do have to deal with the applications of these models sometimes, and I tend to notice that a lot of these applications that are used to provide as tools for modeling. They are built with really old languages, such as Fortran or close to that. And a lot of the dependencies of those libraries are also archaic, and it's difficult to sometimes even install some of these old dependencies. And you end up having to have, a separate runtime environment on a container or something just to make the thing work. I was wondering, could this be used to you were generating tests with the variables as constants. The question is, could all of these dependencies of these modeling tools and the tools themselves be ported to Julia, for example, with the help of Dyad?
Yes, yeah. So I think that's a great question. So I think the first thing to ask is okay, why should we just be using some of these tools on the Fortran directly? Because it's like, if I no longer have to learn how to build these runner scripts, right? Because I could just have the AI write the runner script for me. So why change to simpler languages at all? Why not just keep to Fortran, right? I think that I would start with that question, and I think that what we really see from the Dyad project, again, the paper that I'm referencing here has not quite come out yet. So we're gonna have to wait another week before all the details about like what I'm saying here about how Dyad is like much more accurate than Gemini and Claude and these things. Right? That paper is I know the results, but they're not out yet. But the reasoning behind a lot of the results that we get, though, I think it really stems from the separation of concerns, right? So when you end up writing a lot of this kind of Fortran code, right, you're writing both the model model and its implementation together, right? You're not writing a code that says, okay, here are the equations, and then a different code that says, oh, here's how I compile these equations to work with a GPU, right? The code has, here is how I do the SIMD, here's how the right way I'm going to do the loops, here's how, everything about the implementation is mixed with what is the actual equations of the model, right? This is something that many other people in this room have talked about, right? This separation of concerns aspect. I think one of the things that we're really seeing is that if you do not have separation of concerns, these AI agents get really, really messed up because they start wanting to do things like, oh, I want to change this equation. But if you want to change this equation, suddenly it's like, oh, I need to change the way that I'm putting things on GPUs. I need to change the way that I'm, MPI distributing everything, right? And so if you have, it starts to mix it up because you can no longer make small changes at a time. You have to make very global changes in order to do anything, right? And so what we're seeing is that, what we're seeing then is like you could maybe start to use these tools on these kind of Fortran models, but the lack of separation of concerns, that mixture of implementation with the model itself, really ruins the accuracy and the ability for these tools to work. So this then gives us the reason to be moving a lot of things to Julia and Dyad, which is that if we can construct programming languages for which the implementation is so like whether you run it on GPU or CPU is separated from how the model is actually written, right? So you say, oh, I have a vectorized piece of code, and if I give it a CPU array, it runs on CPU. If I give it a GPU array, it runs on GPU, right? That separation of concerns makes it much more easy for the agent to be accurate. And so then because of that property, then trying to take a code and using these tools to do the translation ends up being helping, right? Now, using these tools actually came first, like the first places where large language models were used was actually for language translation, right? I mean, it was used for Google Translate, which is, English to French and English to, to Portuguese and all this, right? So it's kind of a different problem, but it does mean that these tools do end up doing quite well at language translation. But what you normally want to do is, again, they only work doing small things at a time. So doing something where you say, okay, translate this file to do the direct translation of it from Fortran to Julia, and then you say, okay, now test this. Now after I get this, well, I probably don't want to use for loops. Change the for loops into broadcasts, and slowly merging it to being something that's more general. That is an approach that seems to do fairly well. In fact, the thing that I'm skipping over here because of time is we actually have that the other thing is translation between different modeling languages as a part of the Dyad system that's actually been able to do so. It has a whole corpus of different models and how to do the translations, some manual steps in there, et cetera, et cetera. And so we actually using this for doing translation to simpler languages to then allow the agent to run on it on the simpler language is one of the main use cases that we are seeing for this in the future. If I had more time, I would go into that bit as well. I'm talking about this from Modelica to Dia, but it's also the same thing of changing from Fortran to Julia. I mean, you can use the purely open source or the purely Claude, Gemini to be able to do this. If you use the pure ones like that, I would say you probably want to create your own pipeline, which tells it to do it step by step and breaks it down into just do a direct translation, now change the loops, now change this, now change this. It'll be a lot more effective than to say, oh, translate it and turn it into nice Julia code, right? If it doesn't do it step by step, it will fail. But they do well if you do break it apart.
I would say test by test, right?
Yeah.
If you want to translate effectively, you will get the old system. You will get a huge battery of tests to characterize the old system, and just make sure the new one is in accordance.
Yeah, and in fact, what we do with the Modelica to Dyad kind of engine, and you can kind of build this on your own for very specific kinds of things, right? Is we say, okay, take the original code that you have, now build a binary of the original code. You can use that binary as a source of truth, and then build a bunch of unit tests, just putting in random values into here, and so that way we can know how close it is to this source of truth over a wide space of parameters. And now, as we do the translation, translate one piece of the code at a time, and be inputting C calls and things, so that way you're still using a lot of the original code, and one piece at a time, get one script correct, and now it's matching all the values, get one script correct, one matching all the values, and if you slowly make it so that way it's pipelined that, then it's able to be fully automated. If you try to tell it one shot, do the whole translation, it's going to fail every time. So, I mean, especially with Fortran, right, you can do this nicely with Julia because, you can C call into Fortran, so you can say, hey, here's all my, now expose all of these functions, create a binary that exposes all these functions, now translate this function in Julia, but then replace this function right here with a C call to the original Fortran code, write unit tests here. Okay, I got this function correct, do the next function, do the next function, do the next function until it's all correct. That ends up working quite well, yeah.
Yeah, so it's sort of a related question, but essentially it is, what do we call the Julia language? Because in your presentations, you've emphasized the need to put constraints around things. Mm-hmm. Julia has this great power that it allows us to abstract things in many different ways. That becomes a potential source of difficulty, because the language itself, if you include especially the effervescent development that happens outside of the Julia world, is never defined what it is. Right? It can be any kind of thing ultimately. So what's your sort of sense of that? What is the Julia language?
Fantastic question, right? And I think it's evolving. I think because of the way that these LLM tools are changing how we do programming, I think it's actually changing what we're thinking the right language has to be, right? I think that Julia has the right baseline for this, right? And the reason for this is that you can think about Julia as a gradually typed language, right? Where it's a language where you say types are not required, but you can start to put types in there and have type information, right? And I think that's exactly what you kind of need for these agents to start to work, right? Because if you take it and put it on the system, kind of like Rust sometimes, right? It will be very difficult for it to figure out how to get the first thing to run and compile, and it might give up halfway. That's kind of difficult for it, right? Now, if it tries to start writing something like Julia code, sometimes it will just, it'll create bad Julia code to start. It might allocate a lot or something, but it'll get the right answer, right? And this kind of property helps the agentic system work a lot, right? Because what it needs to do in order to do this iteration process is it needs to be able to write a bad code that gets the right answer, and then make it more performant, and then make it so that way it's type stable, and then add allocation testing, add jet testing, et cetera, and slowly turn into something that's more static, right? And so you can actually see this live happening. I mean, it's probably happening as I speak inside of the ordinary DiffyQ repo, right? I mean, some of the things that it just came up with is just saying like, there's some jet tests. It needs to add jet tests to be able to make things more static, right? And so it's live trying to just figure out, how do I make things more static? And turn this into something that's more like Rust code, but step by step on different pieces, right? I do think that this is going to change the structure of the Julia language down the line. And the way that I think this is going to look is that I think that there's going to be a subset of the language that'll be like a strict subset that will act more like Rust. And so what you'll be able to do is you'll be able to say, hey, look, the starting point of our language is it feels like Python. And the reason is because it's very easy for the agents to be able to guess what code is like and run like this. But I can merge my code to be something that's now compatible with like trim, making small binaries and things that we heard about with Julia C. That actually has a lot more constraints to it, right? And so what we're doing right now is you can add tests to be able to say, okay, I want my code to be able to still satisfy all this. But I think the last little bit to this is actually just have that be a well-defined subset of language, call it strict Julia, that then you can say, okay, now I want my code to be able to run in strict Julia by the end, right? And so then you can have this process where you gradually go from a code, again, it's all in one language, it goes gradually from a code that's very dynamic to a strict version that then requires static behavior. And in that version, it can have more static analysis. There's actually open pull requests and discussions going on in the Julia repo for what the definition of the strict mode would be. And within Julia Hub, we're already starting to try to build out that strict mode because we need it for some of the things that we're doing in the dyad space. So I believe, so again, there's many ways that the language can evolve or whatnot, but from working with the compiler folks and everyone directly, seeing how we're working with it with the agents and everything, I believe that this is the language of how it's evolving, and I think that this is the language that needs to exist for agentic systems, because it's very difficult for them to get the strict mode perfectly correct the first time, and if they don't have anything, if they don't have anything to start on, they can't start this loop to improve themselves. So I think that is kind of the optimal space there of making something that's easy to hit to get that first version, but also gradually able to get more and more type information, and then lock down and say, okay, now do not accept any code that does not meet these stricter constraints. And I think that Julia will become the language to do that. There's a lot of work that's going to have to come towards that, but I think you can start to see that in things like the Julia C and the trim compatibility, all the jet testing and everything. You can start to see the foundation of this being laid out.